So please check that. I'm sharing my screen, so I hope you see the slide with a summary of problems in gold division. I will wait maybe 1 or 2 minutes before I start discussing anything important, so that a few extra people would join. Yeah, today we are discussing gold problems. We'll try to do it in 1 hour. And in 60 minutes, I'll start discussing the platinum problems. The plan for that as well is 60 minutes. We'll see if I manage to do it in time. Yesterday, we did bronze and silver problems, so you can find that on YouTube channel of XCamp Academy. I will monitor the chat on Zoom and YouTube. And on Zoom, tell me out loud if you also have some question and I don't see it immediately in the chat. In gold, we had 3 problems, and generally problems in USACO, at least nowadays, they are not necessarily sorted by difficulty. I think in every division this year, it was just sorted alphabetically. So you shouldn't assume that the first problem is the easiest. We had 3 tasks: cow traversals, milk buckets, and supervision. And the order of difficulty, I would say, was maybe the second problem is easiest. And then arguably, for me, it was like this: second problem easiest, then third, then the first one was most difficult. But I see how people can swap the first and third. Maybe for some people immediately the first one is, you see how to solve it, and it's only some implementation difficulty, versus the third one, you can for some time not know how to finish it with good enough time complexity. So if you have some other opinions about the difficulty, you can write in the chat. But I will discuss problems in order. So I will go first, second, third, starting from cow traversals. Again, arguably the hardest problem. But maybe not that hard if you have experience with similar problems, including one problem from USACO 2025. I have it open somewhere here. What was that? Reachable pairs. So maybe let me immediately open it. USACO reachable pairs. This one from gold. Problem 2 from USACO 25 January contest. It's related, and it's not the first problem of such type. I will paste in the chat, but also you can search for the name. I pasted in the Zoom chat. Please, somebody copy it into the YouTube chat. But let's see this one. In cow traversals, so first the gold division problem, we have n cows. Each of them is pointing to some other cow, and they will try to go there usually, unless this cow has a party in its own place. Every party has a type of COW. I will from now on just assume that a letter is mapped into a number. So we have 3 numbers possible. We have party of one of 3 types. And if a cow has a party in its own place, she stays there. Otherwise, she follows direction of AI. We need to handle some updates of some party happening somewhere now, and it wasn't happening before. The party stays there unless otherwise changed. And we need to know how many cows will attend party of each of those 3 types. How many cows will go and eventually stop at party of type 2. So they will keep going until they find a party happening. First of all, when we say that a cow I goes to another cow AI, this has a name. It's called functional graph. Functional graph, and we can draw it. We can represent this thing as a graph, where if I have some nodes, or maybe let's first not use numbers, there is no point. From one node there is an edge to another, and so on, and eventually there might be a cycle. So as you can see here, a cycle, and generally, especially in very hard problems, what we should think about is a cycles and directed trees pointing into it, like so. So this is how how a functional graph generally looks like. Okay, there is a cycle. Let me mark it maybe here, directed cycle. And then there are trees, directed trees entering some nodes of the cycle. That's what functional graph is. Not always we need to have that deep of an understanding of this. And in this problem, I think you don't actually need to find those trees and cycles. It's possible to do it without it, but this is good understanding. And every connected component looks like this. So a functional graph means that every connected component is equal cycle and trees going into the cycle. Initially, there is no party happening. So the answer would be that no cow attends no party. If I don't know if that was grammatically reasonable. And now if some party is happening, like here there is party of type 1, then all the cows that are in this subtree, they are attending this party from now on. If this is hard for you to analyze and, for example, to go through a sample, then what might make sense when we have a tree or something more complicated is first to process the statement, to understand the statement, how it behaves, for a line. So if I just had a sequence of cows, each liking the next one, and let's say that at the end, the last cow likes itself. This is a self loop is possible here. Then if there is party somewhere of type 1, there is party somewhere else of type 3, then the answer is that type 1 party is attended by all those cows, type 3 party is attended by all those cows, and finally, the final cows here in the suffix attend no party. We can say that that's party of type 0. And if new party happens, so if new node gets some new party, let's say of type 2, but it could also be of type 1 or 3, then it breaks this part into two smaller parts, because now everybody here will attend the party of type 2, everybody here will attend the party of type 3. In general, you should have, in gold division, I think, you already should have intuition that it's hard in graphs to process connected components or some parts of the graph breaking down into smaller parts that are given to us in queries. That's not easy to do. There are no standard or easy algorithms that can do it. So in particular, something like this has no simple or linear solution. You're given a graph, process a fact that some edge is broken, like, because this is what is happening here. We break an edge, we break an edge, we break an edge, and we need to in some way update the sizes of connected components remaining. That's something we cannot do nicely in a graph. What are our choices to solve this problem then? First, something that I will not discuss, but solution 1, complicated, is to understand that first, I think it's good to go through this sequence and think how you would solve this thing. And how I would solve it is, by the way, with a set or a map, where I would store positions of parties. If I know the order of nodes, and let's say we pretend that those are numbered from 1 to n, then when there is new party happening, then I can use lower bound to find the next party, the previous party, and I will know what was the number of cows that were attending one party a moment ago, and now it's broken into two smaller parts, so I can update the values. That's reasonable. Then you can apply this logic to one of the subtasks. I don't have it is here at the bottom of statement, but there was subtask that it's a permutation. Every connected component is a cycle, so that's also doable with set. And if you want to now solve this for general case like this, so in particular trees, what you can do, or how this behaves, is that for each tree that enters a cycle, you need to process something like this. There is information that party is happening, let's say here. So you need to get the information about size of this subtree. That's relatively easy. So you say, oh, this thing has subtree of 10. You pre-computed that, easy. But now, if there is another party happening, let's say here, it has this subtree, then the number of cows that will go to this party is equal to this thing, the size of green subtree minus size of red subtree. That's already more tricky, especially because a lot of other smaller parties might be happening already. So from this range, a simple version would be, from this range, you want to know the number of, from the subtree, you want to know the number of cows that are not attending any party right now. Actually, it's even more complicated because there might be a party happening here, let's say. So this even bigger subtree. And now when green is the place with new party, what you need to also detect that, okay, everybody here in this area, a moment ago, those cows were, again, this is the tree directed up. Look at this thing. The arrows point towards the root of the tree, and this is how cows follow until they see a party. Okay, so everybody from here, let's say from this highlighted place, they will keep going up to a parent until they see something. So now, a moment ago, without this green thing, everybody here went to the red party. Now they go to green. So I need to, in some way, detect what is the size here, number of cows that go above the green guy to the red guy, how many of them there are, I need to detect. I need to mark them that now they are going to the green party, and I need to update the answer for red and for green party. That's quite some work, but it is possible. I think heavy light decomposition might be useful, but I would not use it. So maybe optional heavy light decomposition, question mark. I wouldn't use it myself. I would use Euler tour tree and segment tree that can do something with ranges. And most likely a lot of things are happening with ranges, so I think lazy propagation cannot be avoided. Or maybe it can be avoided, but I think most solutions should have lazy propagation here. Euler tour tree is the algorithm that flattens the tree into a sequence. So now subtree becomes a range, and we can actually query or update ranges. Also, I'm going to, okay. Now, I told you, this is a complicated solution. And I saw in Discord that some people did it this way. Well, good for you if you managed to get the full score, but it was a lot of work. What I will discuss in detail is second solution that is much simpler. And I already was telling you, oh, and even in this thing, I didn't tell you the details about cycles. So I said that there are trees. I told you what we should do on a tree, but we actually have a lot of trees and they go into a cycle and something happens on a cycle. So it is really a lot of implementation. I would guess that on average, it would be 259 lines of code. So my estimation, 250 lines, maybe more, depends on how much you think about it. Then second solution has a lot to do with what I said here, that as an experienced participant, as somebody in Gold, you should already by now know that breaking connected components into smaller parts is very difficult in graphs. But the opposite is easy. It's easy and it's solvable to merge connected components into bigger parts. And so whenever problem is equivalent to our queries, breaking edges, disconnecting components, so making smaller parts, very often we should do things backwards. So we are going to solve the problem offline, which means we read all the queries and then we process them backwards. Go backwards. And as you go backwards, the connected components will merge into bigger parts. So we will use DSU, disjoint set union or find an union. Let's see how that works. Do I have... I'm looking at a piece of paper to see if there is a particular example that I want to draw. Okay, let's see. Let's say that there is some small cycle. Looks like this. And maybe at least this node. There are some other nodes that are entering it. That might be enough for now. And we go backwards. It's not necessary in implementation, but it is possible to assume that at the end, everybody has a party. So you can read all the Q queries, and you can add n fake queries. Each of them is saying that every cow has some extra party at the end. It doesn't modify the answer for those queries here, because if you think about what the statement represents, it says you need to go through Q queries one by one and at every time say what is happening in total. The fact that you add some extra queries at the end doesn't change anything. So for convenience, if I didn't worry too much about the constant factor, I would add n queries at the end, one for each node, saying there is a party of the first type happening there. Because of that, as I go backwards through those queries, I can assume at the very end, everybody has a party. So maybe let me copy this graph, if this is technically possible. Okay. And before that happens, I might want to maybe mark nodes. So it would be easier for you to see. Okay. Now let me make a copy. And what happens at the end is everybody attends their own party. So the graph actually looks like this. Everything is its own connected component. So for example, this is a party of size 1. This is a party of size 1. We now go backwards. And let's say that I will for a moment assume that all of those are normal queries. So I will not do something special for those n. Actually, the only thing special that you need to do for those is not output the answer at the end. You need to save answers, but then going forward, only output answers for those Q real queries. Let's say that there is party of type 3 happening here in this node. And this node is here in my right drawing. If now we say that this party is not happening anymore, and now I need to say there is no party here, then it means that the cow from this node will go to its parent. So that means that those two nodes merge. If a moment ago, those two cows had some number from 1 to 3 describing the party that they were attending, now what I need to do is merge those two. So those two I merge into one connected component, and I forget about this party. I need to decrease the answer of type 3 by 1 and increase the answer of the party of type 1 by 1. So in particular, what I maintain is this, an array of size 4, where at indices 1 to 3, I maintain the answer of how many cows are attending party of each type. So now this is one connected component. Let's say that later maybe some other two nodes merged, maybe those two nodes merged, and they have a type 2. Let's see what happens. So this corresponds, by the way, to erasing few nodes like so. Okay, let's see now what happens if I keep going backwards and something tells me, yeah, in this suffix that I went through already, this thing had a party, but now it doesn't anymore. So I remove this guy. So it means I need to process its edge to a parent, so this thing. So those two nodes I need to connect into one connected component. Let's look at our graph that we maintain as we go backwards. So this is the graph from the input, and this is the graph that we maintain going backwards. This is the DSU graph. I need to merge those two things. So I tell DSU, merge the connected components or groups of those two nodes. And in part, the type of the party that stays is the type of the parent. So In the merge function, I have the merge function of DSU looking like this. And here the order is important. For example, I can always first provide child and then parent. And what happens is the type of the party where group X appears, we need to decrease the answer for this type. And for type of this party, we increase the answer. Okay, so I ask DSU what is the, the root, the representant of this group. I ask about its type. Its type happens to be 1. So I decrease the answer of 1 by something. I then erase that. And I connect those two groups. I mean, it doesn't even need to be this edge. DSU will not necessarily connect those two with an edge, right? But in some way, it will connect those two things into one connected component. So long story short, now this is connected component of size 4 and the party type 2. For every connected component, other than standard stuff for DSU, you certainly need to maintain size, where some DSU implementations don't do that, and you need to remember the party type. So those two things. The party type also can be 0, which happens if, let's see when this starts happening. Well, intuitively, the party is of type 0, so no party. If we go forever in a cycle without a party. And as we process things backwards, the moment it will happen is when the last item from a cycle is cancelled, the last party in a cycle. You might think that because of that, we need to detect cycles. Actually, that's not the case. As we keep processing the updates going backwards, the cycle will close automatically, and in DSU, what will happen is that this is the moment when we try to combine two things from the same connected component. Right? Because each of those, look at this drawing on the left, the input graph. If every node appears once as losing a party as we go backwards, then every directed edge will be processed once. And in this thing, every edge, it combines two new things, except for the last edge of a cycle automatically. So in the merge function, what you want to do is usually we start like this, get parent of X, Y is get parent of Y. And now if X is equal to Y, then we are finishing a cycle. So change type of this connected component or party of this connected component into 0 and then return. Otherwise, we do the standard merging thing where we combine two things. And this means this cycle a moment ago, and maybe some parts that were connected to this cycle, they had some party a moment ago as we process backwards, and now it doesn't have any party anymore. So I just decrease the answer of 1, 2, or 3 by the size of this connected component, and that's it. And I change the party type into 0. And what else? Finally, in the input, a node might have multiple parties of different type. So if in the input, it tells you node 5 at time equal to 3, it has parties of type 2, then at time equal to 10, it has party of type 3, and time 15, it has party of type 2 again, and so on. As you process things backwards, keep in mind that all of those events, they are not erasing a party, only changing the type. So when each of those things happens, then you know that only you need to look up the connected component of this node and change the party, so also modify the answer. But only from the input, the first occurrence of a node, or as we process backwards, the last occurrence of a node, only then this is actually erase, which triggers the merge. So only at this thing you merge, at those things you only modify. And that's it. The time complexity, Q plus N times log. It might be even smaller log because DSU has sometimes log star instead of log, or maybe log. I don't even remember, some small logarithm. Um, so that's the easy solution. And it's something very common. Whenever you realize that it's a graph where edges disappear and you need to maintain info about connected components, you should immediately think this. I want to do it offline, backwards, with DSU or something similar. Tell me if you have any questions. Mm, 27 minutes. I'm looking at the time to see if we'll manage to do gold problems in 1 hour, but I think so. This was, for me, it was the hardest problem. Don't know about you. Party zero. I see a question about party of zero. I'm guessing either you are asking about party equal to zero or about answer of zero. So let me tell you two things. Answer of 1, 2, 3 are things that we will output. Answer of zero is something that we never touch and we can ignore it. Or even if you modify it, you never output it. But with this, you could track number of cows that don't go to any party. And regarding the type that we store for a connected component. So for every connected component here in the drawing with red, I showed you the type of a party. But as we process backwards, eventually a cycle closes. So then we can here maintain party equal to zero, meaning that those cows, they do not attend party of type 1, 2, 3. They keep going forever in a cycle. So that's what party equals zero means. What do we have next? Milk bucket.